Okay, I don't see Chad or Sally. The lab posters need to be completed by Cassie. You told me, right?
April 15th.
Yeah, April 15. By tax day, if you will. So work on those. And we are going to continue from where we left off last class period. So last class period we left off with Xrays. And so we talked about the continuous part and the discrete part. What do we call the continuous part? And of course you can read it. Bremsstrahlung. And what causes this Bremsstrahlung? It could be collisions or near misses with nuclei. It's caused by the slowing down and thus acceleration of charged particles. And so that Bremsstrahlung radiation has a maximum frequency or minimum wavelength corresponding to the entire energy of the incoming electron being converted into, it's electrons, of the incoming electron being converted into a photon. And so, since the energy of a photon is E is equal to HF, or frequency is C over lambda, so HC over lambda, then we can say, okay, so if the kinetic energy was, let's say, 100 kiloelectron volts, HC over lambda, I could calculate what the wavelength is, or I could calculate the frequency. Now H, I just told you last class period, I think that H is Planck's constant. It's a number. The value for H is 6.626 times 10 to the minus 34 joules times seconds. For lab tomorrow, you're going to be doing the photoelectric effect experiment. The experiment that Einstein proposed to show that light had a particle behavior. And one of the outcomes of that experiment is going to be calculating this constant. So just doing that, if I take my 100 kiloelectron volts as HF, I can find what the frequency would be if it's all converted from kinetic energy into light. So I would have 6.6. Divide both sides, of course, by 6.626 times 10 to the minus 34 joules times seconds. What do I have to do besides that? I've got to do some unit conversions. If I forget about my unit conversions, I'm going to be in all kinds of doo-doo. And so, what is an electron volt? Okay, that is a correct statement, but putting it more simply, it is the charge of an electron, 1.602 times 10 to the minus 19 coulombs, multiplied by 1 volt, which is a joule per coulomb. Well, those coulombs are going to cancel, and 1 electron volt is 1.602 times 10 to the minus 19 joules. So there's a simple conversion. Now this is a kiloelectron volt. That means 1,000. So I'm going to have 100,000 electron volts times and what do I find for my frequency?
2.42
times 10 to the 19 hertz. That is a huge frequency. Does anybody remember the range for visible light?
Like 400 to 700 deal?
Okay, 400 to 700 nanometers, or in frequency, I actually went 400 to 750 because that allows me to keep the same numbers. Visible light is 400 nanometers to 750 nanometers, or 7.5 times 10 to the 14 hertz to 4 times 10 to the 14 hertz. So this is, 5 orders of magnitude above visible light. So it's pretty high frequency. But we can calculate what the cutoff should be just based on converting all of the kinetic energy of the electron into a photon. And then the rest of the structure, this graph here that shows frequency as a function of the number of photons, shows you that you have a fairly linear conversion up to a point where it then drops off from the breaking radiation. Okay, what about those line spectra, also called the characteristic peaks? What causes those? Yeah, it's electrons that are bound to the target falling to a lower energy state. Why? Because an electron had to, for that to happen, an electron had to come in and actually interact with a tightly bound electron and free that tightly bound electron, or at least raise it to a higher energy level, leaving a low energy state available. And then some lucky electron says, whee, I'm going to the lower energy state. And when it drops to lower energy state, the difference in its energy is given off as light. And so these characteristic peaks are the peaks from electrons falling from like n equals 3 to n equals 1. And the last thing we went over in class on Friday was the nomenclature. If it is a K, that means that it ends at n equals 1. If it's an L, then it ends at n equals 2. And of course, M would be 3, right? KLMN adds up nicely. And alpha means it's a transition, a difference of 1. So going from like 2 to 1. Beta is a transition of difference of 2, so going from like 3 to 1. So that's how those are labeled. Now that's almost ending my X-ray discussion. We'll come back and talk about medical X-rays. But any questions about X-ray production before we move on?
So this is kind of a stupid question, but on the homework it said something about like X-rays, like the X-ray machine produces X-rays, and they're just X-rays and photons are the same thing, right?
Right. X-rays are photons produced by having electrons smashing into a target. Gamma rays are photons produced by interactions inside a nucleus. They can have exactly the same frequency or energy. It's the source that makes the difference.
So you're saying there's no physical difference between the two then?
There's no physical difference between an X-ray and a gamma ray. Now, gamma rays tend to be higher energy, higher frequency. X-rays tend to be lower energy, lower frequency, but they can overlap. And it's the source that makes the difference. So, outcome of this, Einstein said we can treat light as if it's made up of particles. You have a beam of light, like you turn on your flashlight. It's kind of like you fired a shotgun. You fired a whole bunch of little particles of light that are called photons. And each photon has an energy of hf, Planck's constant times frequency. Or like I wrote on the preceding slide, since frequency is speed divided by wavelength, you can put it's hc over lambda. We use this enough that we like to calculate this number. H times c is 1,240 nanometers times an electron volt. That makes it really easy to convert from energy to wavelength. So for instance, when I was in graduate school, for my PhD research, I did most of my research with a 248 nanometer laser. 248 nanometers, is that visible spectrum? No, it's not. This reminded me, I wanted to, while I was on here, put some lines on here that I never did. Don't worry, I'll get there. I actually have this open, so it won't be as bad as it seems. 248 nanometers is ultraviolet. And so I could take, for my research, and just say, well, my wavelength is 248 nanometers. Therefore, the energy of each photon was equal to 1240 nanometers times electron volt divided by 248, that looks like a 0, by 248 nanometers. And that gave me an energy of 5.0 electron volts for each of my photons. So each photon had that energy. Now that energy is pretty high. That energy is enough to break bonds in materials. So what was I studying? I was studying how you vaporize materials with light. But I was studying materials that are transparent. So I have enough energy to break bonds, but if it's transparent, that means the light should be going straight through. So that's why it was research worthy. Okay, some energy things. We have a spectrum shown here, and we have radio waves, infrared, ultraviolet, and so on. But in our textbook, it shows us a table of energies that are important. And the first thing is rotational energies and molecules. Rotational energies and molecules start right about here. That is, if you have a photon with an energy above that red line, it can make molecules rotate and excite them to higher rotational states. Why is that important? Well, note what part of the spectrum that line is in. The microwave spectrum. The discovery of microwaves, I've read too many variations on this to know the truth anymore, but the basis of the story of how microwave ovens were invented was researchers working on microwave radar, and the guy puts his lunch bag on top of the, what is it? Can't remember the name now. The thing that produces the microwaves. And when he comes to eat his lunch, depending on the story, either his chocolate bar is melted or his sandwich was warm. But he noticed, wow, my food got heated up by sitting on this, but it's cold. And so how did the food get heated up if it was on a cold surface? And so they started studying, and they realized that these microwaves are in the right region to make water molecules start to rotate. And so you're transferring energy from the photon into kinetic energy, rotation in the molecules, which then gets distributed out, and you cook the food. And so that's the mechanism by which microwave ovens work. They're causing water molecules essentially to rotate. So you put something in there that doesn't have much water, it won't absorb as much. Something with more water will absorb more. They're using microwaves. If you put something that's metal in there, what happens in the metal? Well, you have electrons that are free to move. And then you're putting these high energy electromagnetic waves that make the electrons zip back and forth and absorb huge amounts of energy. That's why it's bad to put metal things in the microwave. Okay, the next one on here. So this first one was rotation. Actually, let me put it below. If you go up to higher energy, like 0.1 electron volts, so somewhere around here, then you have enough energy to cause vibration. So that's making molecules go like this. And so that's another way then that you can have energy absorbed by a material. So you know, if you use waves that are somewhere in the infrared, you might be able to cook with that as well by inducing vibrations. Notice the radio wave section. Something that's important about the radio waves, I shouldn't use the same color. That cutoff for the radio waves is the cutoff for what we can make with microelectronics. We can make oscillators that make electromagnetic waves up to the top of that radio wave segment. Beyond that, we can't make them just by making an electronic circuit. We have to have something else to do it. Okay, so we have the vibration there. The next line is where we're getting important. The 1 electron volt range, so 1 electron volt is somewhere around here. That's where we can start exciting / ionizing atoms. Why is that important? Well, that's where we can start messing with what's going on in chemicals, like the chemicals in our body. So if you have sunlight that's above that blue line, it can cause electrons to leave a strand of your body's chemicals. And when that electron leaves, well, then you might break a bond, because suddenly you've ionized an atom that was supposed to not be ionized to bond. And so you can start messing with with molecules. Messing with DNA is considered bad, right? If you ionize something in a strand of DNA and it breaks, it usually just repairs. Usually no problem. But every now and then it will repair incorrectly. Most of the time when it repairs incorrectly, it just dies. But sometimes it's robust. And so, look at me. Hey, everybody, you want to be like me? And it reproduces. If it's wrong and it reproduces, what do we call it? Cancer. So that's the mechanism where radiation is generally considered to be dangerous. When you get up above that ionizing radiation, up above around 1 electron volt for the photon, that's when it can start damaging material and you end up having the potential for cancer production. So a photon that has a frequency somewhere in the ultraviolet range, you notice the transition here is an ultraviolet, may start to become dangerous. You go higher, X-rays, oh yeah, those are in the range that's dangerous. Gamma rays, in the range that's dangerous. Question of how dangerous? Well, I just had X-rays this week, right? Wait, this week? Last week. Last Thursday. I had X-rays last Thursday. Was I concerned? I wasn't. I'm really cavalier about it. When my mom was a child, she loved to go to the shoe store, put her foot in the little machine and it X-rays your foot and tells you what size your shoes should be. They don't use those anymore because they realize, hey, this is not perfectly safe. It's not hugely dangerous, but it's not perfectly safe, so we shouldn't play with it. We still use it for medical procedures because it's beneficial to know that information, and it's a risk versus reward analysis on when we should use these kinds of things. There are a couple more steps on this table. Binding energy of a tightly bound molecule, 10 electron volts. Energy to ionize an atom or molecule. It has 2 levels. It says, yeah, it has 1 for starting to excite them and 10 for ionizing them. But that's where things are starting to get dangerous. Yeah. So there's some important things to know about the energy in a photon. I don't think I have any slides on this, so let me talk one more thing about X-rays. Röntgen discovered X-rays in 1895. Within a year, X-rays were being used in medical diagnoses. Our textbook has a picture of Röntgen's first, I think it was his first X-ray image, which was of his wife's hand. Why are X-rays useful for medical reasons? Okay, X-rays, they're electromagnetic waves just like light, but unlike light, our bodies are transparent to them. Well, some of our tissues are transparent. And so you take an X-ray, and it goes pretty easily through your flesh, gets blocked a little more by the bone. And so you can see differences in contrast from the different types of tissue and how thick the tissue is, because they go through us pretty easily. So different frequencies are, for our bodies, some are transparent, some are not. And the same is true for other materials, hence you can have things like a red glass. It's going to, reflect red light, but transmit the other colors, or, yeah. That's what it looked like in reflection if it was red. Okay, so moving on from that, what causes the characteristic peaks? And I have to change, don't answer yet. Control tab. Okay, you can answer now. Boom. Reagan, Torrey, and Cassie are in there instantly. What causes the characteristic peaks in an X-ray spectrum? I'm a patient man sometimes. There we go. Okay, so we had 9, 0, 2, and 5. Okay, well, the 9 people are correct. I said it on Friday, and I said it again today. You have 2. When you have an electron that falls down from like n equals 2 to n equals 1, it gives off a photon of light. And in this case, what would the notation be if it goes from n equals 2 to n equals 1? K alpha. K because it ends at n equals 1. Alpha because the change in n is 1. So that's a K alpha. That's what produces the characteristic peaks. Now, I don't think I have this as a clicker question. I'll feel stupid if we go forward one slide and we do, and I forgot. What causes the continuous part of the X-ray spectrum? Right. This here is what causes the continuous. And who can remember the crazy name for that? I'm sure that's spelled incorrectly. Like it's got double S, I think. Or, I mean, it's probably written like that, right? But it's the Bremsstrahlung radiation. I can't spell it correctly. I don't expect you to spell it correctly either. But you should know what the Bremsstrahlung is, the braking radiation, the slowing down. And now, please don't be that clicker question. Good. Which statement is true about wave theory? Wave theory is what we studied for the last exam. Didn't take it, Toussaint. Still no answer. Okay. Okay. So half of the answering people said the frequency of a wave cannot change, and half the people said something else. That actually is pretty similar to the way it was in the test when we had the question relevant to this. about half the people said the frequency can't change. Right? You had I think it's question 2, what happens when the light goes from air into water? The frequency has to stay the same, but since it slows down, the wavelength has to become shorter. And so you had to calculate those things on the test question. The tests are all graded. They should be scanned and uploaded to Moodle this afternoon. I haven't tabulated the scores yet, but I have the general feeling that things went better this time. That was a relief to me. Okay, moving forward to Arthur Holly Compton in 1922. He found something miraculously crazy that contradicts exactly what 8 of you just answered. He was hitting a crystal with light, and he found that if the light went straight through, of course he had the same wavelength or same frequency that he started with in air. But if the light bent, that is, if it refracted, changed directions, he had 2 peaks in his wavelength. One that was one was the wavelength he started with, and one was shifted out to a longer wavelength. Kind of a problem, right? Because we just said, for a wave, the frequency can't change. And if you're in air, then that means the wavelength is also not going to change because you're not changing the speed. And so here he has an experiment that shows a clear violation of light being a wave. Well, if light's not a wave, what is it going to behave as according to what we understand? A particle. So this is another example of something that could only be a particle behavior. It's not possible for a wave to stay in air but change its wavelength. So Arthur Holly Compton, I just like to say his middle name, he sat down to calculate what could be going on. And, well, yes, we've already seen that. And let's answer this question before we go to a solution. Which statement is true about the particle theory of light? Choose one to assign. All right. Here we have 3, 4, 3, 0, 6. Okay. Now, this is fine. It's not a problem to me that we don't have even a plurality, much less a majority. Well, actually, we do have a plurality, right? Because that is more than any other answer. We haven't really looked into this yet, so you're just trying to go back to what you've learned about this. And what you've learned so far is that for the particle theory, we have photons that have energy equals HF. And we haven't talked about anything except for that, right? I mean, that's all we've really talked about. But we do know that with the wave theory, we learned that when light goes from air into water, it has to change its wavelength. And so particle theory is going to agree with that. So the wavelength is going to change. So it can't be this one. And if the wavelength changes, then we're going to have, potentially other changes. It turns out that none of those are true statements about the particle theory of light. Because what you're doing is you're treating light like a BB. Can you speed up a BB?
Yes.
Yes. Can you slow down a BB? Yes. And if you speed up or slow down BB, you change its energy, which means that you had to have changed the frequency because they're tied together. If you stayed in the same medium, then you change the wavelength. And of course, if you change the speed, you change the momentum. So all of those things are true for a particle. None of them are forbidden. Or excuse me, they're all allowed. None of them are forbidden. These are all you cannot, right? Yeah, they're all you cannot. So it must be particle-type behavior to explain this Compton effect. So here is a diagram to illustrate what's going on with the Compton scattering. You have a photon that comes in, and that photon strikes an electron, and it scatters away. So we're treating it like a particle. So a particle hits another particle, and they bounce off each other. And in this collision, we're going to have, well, in all collisions, what do we talk about that may be conserved? Momentum. Momentum always had to be conserved, right? And then we had kinetic energy. Now, in this case, we can be a little more clear because we can account for all of the kinds of energy. Energy always has to be conserved. And so we're just going to go straight to energy conserved because we're talking about little particles. There's no such thing as heat in this case because heat is measuring, the average of the kinetic energies of all the molecules. Well, we've got both of our molecules, right? That's just going to be in the kinetic. It's not going to be something special. So what we're going to have is conservation of momentum and conservation of energy. Now in this picture you see that theta is described as the angle by which the photon deviates. So if theta is 0, it goes straight through. If theta is 90 degrees, it makes a 90-degree shift in direction. And phi is the angle that the electron is scattered from the initial direction of the photon. So we have these two different angles. And so we're going to calculate conservation of momentum and conservation of energy. Now if we just look at this, I have this all lined up on the coming slides. But if we do momentum, this is a two-dimensional problem, isn't it? So I'm going to have to do the x direction for momentum. And then I look at this and I say momentum. What's the momentum for a photon? Well, when we studied the electromagnetic waves, we learned that they carried momentum that was equal to their energy divided by their wavelength. Well, for a photon, what's the equation for the energy? See, hopefully I said this all right. Momentum is E over, no, it's E over C, over C. There we go. Momentum is energy over C, so it's HF over C, or, since F over C is 1 over lambda, H over lambda. So I can say my momentum initial is H over the wavelength it started with. Now the momentum final, I have two things carrying momentum final. I have the photon and the electron. And so I'm going to have here a term that's momentum of the electron times cosine of phi plus the momentum of the scattered photon. And I have to take just the x component of that as well. So that's going to be times cosine of theta. So there's one equation that relates the initial wavelength and the scattered wavelength with the momentum of the electron. Now, that's not enough to determine what's going to happen. But it's a start. I can go to the y direction. In the y direction, what can you tell me about my initial momentum? It's 0 because my xy coordinates are shown right here. And you see it was not traveling vertically. And now we just have to choose which one's positive and which one's negative. This picture has the positive being the photon and the negative being the electron, so I'm going to just go with that, minus momentum of the electron sine phi plus h over lambda prime sine theta. So now I have two equations, and I'm relating lambda prime and momentum of the electron with the two angles. There are four variables that I don't know in that bottom equation. In the upper one, there is the same. So two equations, four unknowns. You can't solve it yet. So then you have to go to energy. So if we go to energy, the energy it started with, which would be HF. Well, I don't want to use F because I've been using wavelength. So converting from F to wavelength, that's going to be HC over lambda is equal to the kinetic energy of the electron plus HC over lambda prime. Well, I introduced a new variable, kinetic energy of the electron. Of course, if we were talking non-relativistic, it'd be real simple. Kinetic energy is momentum squared divided by 2m. But if you're doing relativistic, the relationship's not so simple. And oftentimes, this Compton scattering is dealing with the electron leaving at relativistic speeds. So we can't make that simplification. I'm going to cut my math short here. You'll see it repeated on the coming slides, and then we'll get to the actual result from Compton scattering. So here you see the energy conservation equation, and I skipped through, or I went through most of this. The derivation, momentum is photon energy over c, which, if I'd come here, I wouldn't have made the mistake at first, or h over lambda. And so conservation of momentum gives us these two equations. And finally, the result using relativistic energy equations, we find that the change in wavelength, lambda prime is the wavelength of the scattered photon, minus lambda, the initial wavelength, is equal to something there, Planck's constant, remember that 6.626 times 10 to the minus 34 joules times seconds, divided by the mass of the electron, because that's the thing the photon's scattered off of, times speed of light. And then times 1 minus cosine of the angle that the photon scattered through. So this is the result. Obviously, we didn't do the relativistic math to get to the result. But this is what relativity and conservation of momentum and conservation of energy says for the shift in wavelength if light is behaving as a particle. C-I-C-L-E. Now, if we look at this in proper time context, in 1922, relativity, both general relativity that we learned special relativity that we learned and general relativity, those had both been developed. So relativity was already known. And the idea of light behaving as a particle was already known. Compton does his experiment and finds a result that seems bizarre when analyzed with wave theory. So he says, well, let's look and see what particle theory would predict should happen here. And then he looks at the prediction and compares it to his experimental data. So he actually already has the experiment. And then he's all, well, let's see what theory would say if it's a particle. And then he checks his results against that theory. It's a little bit backward in the process because of the way knowledge was gathered, but that often happens in science. And he finds, aha, this is a particle-only aspect of light. This can't be explained with the wave nature of light, only with the particle nature of light. So why do we talk about Compton scattering? Because it's really incontrovertible evidence that light is behaving as a particle, not as a wave. We simply can't have the frequency change if it's behaving as a wave. So, yes, this is just saying, he used the relativistic equations. I have a lot more slides because of the way I did it versus the way I laid it out. That value, Planck's constant divided by mass of electron and speed of light, because it occurs pretty much every time you do a Compton scattering problem, we give it a name. We calculate its value. So it's called the Compton wavelength, clearly named after Arthur Holly Compton. And we can just put in the values for Planck's constant, the mass of an electron, the speed of light in vacuum, and we find that it has the Compton wavelength 2.426 times 10 to the minus third nanometers, or 4.853, doubling that, or you could write that as 2.426 picometers if you prefer to not put 10 to the minus third times 10 to the minus 9. That's a really, really small wavelength. And with that Compton scattering equation, you're looking at the difference in wavelength. So you need to be able to measure a difference in wavelength that is no bigger than 2 times that Compton wavelength. I'm going to go back to where I think I have the Compton wavelength or Compton scattering equation. Right, we have the difference in wavelengths is equal to the Compton wavelength times 1 minus cosine theta. Cosine theta varies between 1 and minus 1. If cosine theta is 1, that's 1 minus 1, and we have no shift. If cosine theta is minus 1, we have 1 minus negative 1, which is a plus 2, and so we have a shift of 2 times the Compton wavelength. So the biggest possible Compton shift that can occur is 2 times the Compton wavelength, which I hope I went back to the right slide here. Yep. So 4.853 picometers. Not nanometers, picometers. If you're looking for a wavelength shift that's measured in picometers, you don't want to send in a nanometer wavelength wave because you're looking for a shift that's really tiny compared to that wavelength. You want to send in shorter wavelengths. So instead of doing experiments for Compton scattering with visible light, they tend to use X-rays. Why X-rays? Because they have a much smaller wavelength, and thus the change is bigger compared to the size of the wave you started with. It makes the resolution better. A problem, yeah, we got time to do it, because this is my next to last slide, I think. An X-ray photon of wavelength 10 picometers is scattered through 110 degrees by an electron. So, as with the test, start with I have the photon coming in. It hits the electron, and the electron cruises off like this. The photon cruises off like this. So I have 110 degrees that the photon is scattered. It says, what is the kinetic energy of the recoiling electron? How would you even attack such a problem? Was it Jerry?
No.
Tori?
Michael, that statement we had relating the energy or kinetic energy of the electron to...
Okay. We'll go to our energy relation, which I'm going to write in the simplest form. The energy of the photon initial is equal to the energy of the electron plus the energy of the photon in the end. Right? That's energy conservation. Or, writing it another way, we could say, well, actually, I'm going to leave it that way. Just going to leave it that way. What do I need to do to find, well, what do I know to start with? I know one of those 3 things. Okay, I know the energy of a photon is equal to hc over lambda. And so since I know the wavelength is 10 picometers, that's going to be 1240 nanometers times electron volts divided by 0.010 nanometers. Changed it. Oh, one more zero. Change it to nanometers so my units will cancel. And so what's the energy of my photon initially? Add two zeros. So that's 12.4 kiloelectron volts. So I know the energy of the photon I started with. I'm looking for the energy of the electron. What can I find with the Compton scattering equation? I can find the change in wavelength and thus, I just forgot the T, and thus the final kinetic energy of the photon. So my Compton scattering equation, 1240, yeah, you're right, 124. I apparently am never going to get there. So lambda prime minus lambda is equal to lambda Compton times 1 minus cosine theta. Put in our numbers. That's going to be 10.0 picometers plus 2.43 picometers times 1 minus cosine of 110 degrees. And what does that give us?
10.0036.
It should be.
Oh, sorry.
Should be
I plugged it in as E minus 3 instead of 1.
Should be a little bigger than 12, like 12.5-ish.
I plugged it in nanometers instead of picometers.
Somewhere between 12.5 and 13.
Yeah, 13.26.
13.26. So we have the new wavelength is 13.26 picometers, which means EP prime is equal to 1240 nanometers times electron volts divided by 0.01326 picometers.
93,514.
It's how much?
93,514.
So 93.5 kiloelectron volts. And now we can answer the question. I know and so I just have to subtract. So that's an example of how we can use Compton scattering in real life. Now, we did Compton scattering off of electrons. Does it have to be electrons? No. You can have Compton scattering off of a neutron or a proton. But how's the mass of a neutron or proton compared to the mass of an electron? It's like the proton or neutron is around 8,000 times bigger, if I remember right. Something in that ballpark, which means that the wavelength for scattering would be smaller by that factor, virtually impossible to measure. It has been measured a time or two, but it's really precise. So we usually just worry about it with electrons. The point of it being, it illustrates, once again, particle nature of light. For our last clicker question, which phenomena support a particle theory for light? So this is multiple answers, not just a single one. Put in all the correct answers and hit enter. Okay, so we had 12, 2, 9, and 3. The majority are correct here. Compton scattering was clearly, that's all we've looked at today. Hopefully, I had hoped everybody would realize that's what we've been talking about today, was particle theory. The photoelectric effect, what Einstein got a Nobel Prize for, particle theory. I believe Compton got a Nobel Prize for this as well. Rayleigh scattering and Young's double slit were things that can only occur if it's a wave. Remember, Rayleigh scattering, you have light coming through the air, causes electrons and molecules to oscillate with it and then re-emit light. Okay, have a good day. I'll see you in lab mañana.